Morning, everybody. Hope you're enjoying Friday so far. I am traveling today to go to another conference to learn about IB, International Baccalaureate stuff, so I'll tell you all about that when I get back. But the next progression that we're going to go through here in our journey through two dimensions is now we're going to start dealing with forces in two dimensions. The previous chapter, the projectile motion chapter, introduces us to motion in two dimensions. And one of the things that I wanted to make sure that I instilled upon you is the fact that when we're dealing with concepts, concepts don't change whether we're in one dimension or two dimensions. The idea that gravity accelerates things and all that we talked about when we dealt with motion, those kinds of things don't change. And that's true with forces as well. The concepts dealing with force don't change. But the way that we handle them, the way that we define them, or the way that we address them mathematically will change. And that's how moving from one dimension to two dimensions becomes somewhat challenging. But, like I said, if we keep our eyes on the concepts and what we're really dealing with, hopefully that will make the transition a little easier. So, before we get into actually doing problems, let's review a couple of those concepts. So, back when we were introducing forces in Newton's laws, we dealt with a couple of terms. So the first term we dealt with was inertia, that idea that objects will continue on in their current state of motion. And that led us to Newton's first law, that an object at rest remains at rest, and an object in motion continues in motion with a constant velocity until it experiences a net external force. Hopefully these things are sounding familiar. We've talked about them before, and we said that Newton's first law can be also summed up with this term, right? Equilibrium, where when the net force acting on an object is equal to zero, an object is said to be in equilibrium. And the acceleration of that object will then be equal to zero. If net force is zero, acceleration is zero. And that means that object will remain at rest, or it will continue in motion with a constant velocity. So, last term, before we get into the stuff we're doing here, right? Net external force. This idea of sigma F, the sum of all external forces acting on an object. We did this all in one dimension, and it was great, and we talked about how it applies, and I think a lot of you understand those concepts. Now just remember, moving from one dimension to two dimension does not change the concepts. Those ideas of inertia, equilibrium, net force, they still all remain the same. How we address them mathematically is the thing that changes. So, to get us started, I'm going to go to page 152 of your textbook, and up at the top of page 152 of your textbook, there's a couple example problems. So the first example problem, once again, just to review, this is page 152 of your textbook, and we are looking at example problem number 3. So it says, two ropes pull on a ring. One exerts a 62 Newton force at 30 degrees, the other a 62 Newton force at 60 degrees. So two questions here. What is the net force on the ring, and what are the magnitude and direction of the force that would cause the ring to be in equilibrium? So first let's handle part A. Part A says, what is the net force, right? That's what it's asking us for. So part A is asking us for sigma F. We just reviewed that net force represents the sum of all external forces acting on an object. So we need to find out the sum of the forces. First thing I'm going to do, I'm going to set myself up a frame of reference, a coordinate system, just like we did in one dimension. But in two dimensions, we have to modify our coordinate system because we have to account for both the horizontal parts and the vertical parts. So when we move into two dimensions, wrong one. When we move into two dimensions, our coordinate system now is not just a number line with a positive and negative direction. Now, it's a coordinate plane, an XY axis. So first thing I'm going to do is I'm going to group these together because they don't move. And then, just to make it a little easier for us, I'm going to make those dotted. So there's our coordinate system, our xy axis. And similar to what we did in math class, there are 2 dimensions here. So we've gotten ourselves a way to account for those 2 dimensions. But in the 2 dimensions, in those 2 dimensions, remember, they are separate from one another. They occur simultaneously, but they can be addressed separately. So along the horizontal axis, or generally we refer to that as the x-axis, right? We have 2 directions. We have a positive side and we have a negative side on the x-axis. And then on the y-axis, we have a positive side and a negative side, just like in math class. Nothing different there. So that is our first thing we do, set ourselves up a frame of reference. So now I'm going to group all these together because we'll use that later. So there's our frame of reference. Okay? Now, things we know. So we have 2 forces here, right? It says one exerts a 62 Newton force at 30 degrees. So F1 is 62 newtons, but there's some additional information there, that 30-degree number. And then it says that the other, a 62 Newton force at 60 degrees. So F2 is equal to 62 newtons as well, but it's now at 60 degrees. So putting those on my coordinate system, I've got one that looks kind of like this. And generally when we talk about 30 degrees, 60 degrees, just like in math class, we'll call the positive x-axis 0 in most cases. There's other ways that you can define that, but in your book chooses to call the positive x-axis, so this line right here, 0 degrees, and then go counterclockwise. So this is 90, this is 180, this is 270, etc. So we know that this is 30 degrees here. And then we have this 62 Newton force at 60 degrees, so something that looks kind of like this. If I draw them right, those 2 lines should be the same length, but when I go to put them on my drawing, right, this is going to be 60 degrees right here. Okay, so we go ahead. First thing it asks us to do is find the net force. Like we said, reviewing. Net force, the sum of all external forces. But in the past, all we've done is just add those 2 numbers together. We can't do that when we're in 2 dimensions, at least not with vectors that are set up like this. Just like we did in the last chapter when we were adding those 2 final velocities, you can't just add the 2 of them together. So, mechanically, this is what we do. Okay? Regardless of how you do it, we're going to set our vectors up in a sequential order. It doesn't matter which one comes first or which one comes second, but we line them up so that we start with one vector. I'm going to start with this red vector. And then the second vector is going to start where that first vector ended. So I'm just going to put it just like this. This 60 can go along with it, and that's going to be important in a little while. But the net force now is defined as the vector that starts at the beginning of the first one and goes to the end of the last one. So in this case, we've only got 2 vectors. So my net force is going to run from here to here. We talked about this vector in the last chapter with projectile motion. We refer to this as the resultant vector. The resultant vector is a vector that represents the sum of all vector quantities. In this case, because we're dealing with 2 forces, this is the sum of 2 forces, or the net force. So we need to find the value of this purple vector, and that will give us the resultant of these 2 vectors, or the sum of the 2 forces, which is what this question is asking us for. Now once again, you can't just add the 2 numbers together. You can't just go 62 plus 62, 124, and be done with it. In the last chapter, we found the resultant vector of 2 vectors. But, if you recall, the two vectors in the last chapter were set up like this. Here, and then here. And the resultant of that one is still the same thing, beginning of the first, end of the last. But in the last chapter, that resultant vector was the hypotenuse of a right triangle. And that's easy to find using Pythagorean theorem. This vector is not the hypotenuse of a right triangle. It's the longest side of a triangle, but because of the angles that these vectors were given to us at, or the angles that they're acting in the problem, this is not a right triangle. Now, if you remember law of sines or law of cosines from math class, and I never can remember them, you can use that. You can find the side of this triangle if you know the other two sides and some angles, and you can do some math and figure it out. That's fine. But there's another way that makes use of maybe some simpler ideas, less to remember probably, that will allow us to find the value of that side. And the first thing it involves us doing is, just like in the last chapter, we need to find the component vectors. If we take this red force, so this red force, 62 newtons at an angle of 30 degrees above the horizontal. That force isn't horizontal or isn't vertical, it's actually a combination of both. We said that if we have this force drawn on the picture like this, it's really doing two things at once. It's pulling horizontally like this and vertically simultaneously. It's doing both of those things at once. The end result of that is that vector that we've shown there. This blue vector, once again, given to us as 62 newtons at 60 degrees above the, or at 60 degrees or 60 degrees above the x-axis. That vector is not pulling horizontally or vertically, that vector is not pulling horizontally or vertically, it's pulling horizontally and vertically, simultaneously. The end result of that is this blue vector, 62 newtons at 60 degrees. Now, we've handled this situation before. We introduced this idea of component vectors. Ooh, thought that would be together. We've introduced this idea of component vectors in the last chapter when we talked about things being launched in an angle and that kind of stuff. So here's what I'm going to do. Just for the sake of clarity, I'm going to take this vector and bring it over here. And I'm going to take this vector here, and I'm going to take this vector here. It's a lot easier for me to do because I can move them around just like that. You might want to just draw them separately on the side of your paper, or if not, okay? So, we said we know that this is 62 newtons, and that 62 newtons is a combination of both this horizontal vector and this vertical vector. And if you remember from last chapter, this is what we did, right? We slid this one over here like this. Now, because this is horizontal and this is vertical, this is a right angle. And now that 62 newtons is the hypotenuse of a right triangle. We can do the same thing for this 60 newton force like this. That 62 newton force, the blue force. The blue force is a combination of both this horizontal one and this vertical one. We slide this one over this way. Because this one is horizontal and this one is vertical, x-axis, y-axis, we know that this has to be a right triangle as well. Now, and in the problem, it was given to us that that blue force is 62 newtons as well. Now we've got two right triangles where we know the hypotenuse, we know one of the angles, and we can figure out the other two sides using our sine and cosine trig identities. So why don't you do that now? Just to keep things rolling here, I am going to give you, hold on. Didn't work as smoothly as I wanted it to. I am going to give you 1 minute to do that. So, on your marks, get set, go. All right, so if you were clever enough to remember some things from geometry class, that makes doing this job a little easier. 60-30, I can't remember what we call it, complementary angles, whatever. But because they add up to 90, their sides are similar. So in doing these calculations, you should have gotten 31 for this side here and 53.7 for this side here. But then that means you also should have gotten 31 for this side here and 53.7 for this side here. Okay. What we have done now is we have taken this solid red force and broken it down into the equivalent forces that exist on both the horizontal and the vertical axis. Same thing with this blue force. Remember we said the solid blue is a combination of these two. So what we did was we just basically removed the solid blue and replaced it with those two dotted blues. Why is that important? Because now we've got things that are all either on the x-axis or the y-axis. Relating it back to our problem, if we take this horizontal component, which we know is 53.7 newtons, and we take this horizontal component, which we know is 31 newtons, we can make ourselves one big horizontal component. If we take this vertical component, which we know is 53.7 newtons, and we take this vertical component, which we know is 31 newtons, we can make ourselves one big vertical component. But more importantly, to the problem itself, check out where those vectors start and end. They start at the beginning of the purple vector, which we said ultimately is what we're trying to find, and they end at the end of that purple vector, which we said is ultimately what we're trying to find. Because we've broken these large vectors down into their components, everything is now either on the x-axis or the y-axis. Guess what? That makes this one big right triangle. And you guys know how to find an unknown side of the big right triangle. You now know two sides of that right triangle. I'm just going to move these out of the way. And knowing those two sides of the right triangle, you can figure out the third side. You use Pythagorean theorem to find the third side. So, first, let me give you... This is probably going to take longer than it's going to take you guys to actually figure it out, but 30 seconds to find the unknown side of that triangle. Go. Okay, in using Pythagorean theorem to find the hypotenuse of that right triangle, hopefully you found that this is 119.8 newtons. Now, here's where we go a step further than what we did in the last chapter. That's great. This is the net force. That is the combination of 62 newtons at 30 degrees and 62 newtons at 60 degrees, except force is a vector quantity, meaning it has direction. Now, this one's pretty easy to do, but that means we have to find this angle theta right here, because it's okay to say that there's this many newtons acting on that ring, but you got to give me a direction. Which way are those forces acting? Now, because of the angles and the chosen values of the vectors, this one's pretty easy, right? You have a right triangle that has two sides that are exactly the same. If you remember geometry class, that means that you have a 45-degree angle here. So, for part A, the net force, we would say the net force is 119.8 newtons at 45 degrees. Or, if we do sig digs, we'd go 120 newtons at 45 degrees. That's the answer to part A. Now, taking that, let's apply it to part B. Okay, so, I am going to take this and keep some of the things that we did and get rid of some of the things that we did. So first, I am going to get rid of all this and say that we know that the net force is equal to 119.8 newtons at 45 degrees. I know the angles aren't right, but that's okay. I'm going to get rid of this one. I'm going to get rid of this one. Okay. Now, for part B. Part B says, what are the magnitude and direction of the force that would cause the ring to be in equilibrium? So, we are looking for a force. That special force that would cause the ring to be in equilibrium. And that means that when we're all said and done, the net force on this ring has to be equal to 0. Because, reviewing our terms from before, right? Equilibrium is when the net force on an object is equal to 0. That concept doesn't change. How we define it in 2 dimensions does change a little bit. So, the force that we would act on this ring to cause this object to be in equilibrium, we refer to as the equilibrant. Sounds smart just saying it. The equilibrant is the force that would produce equilibrium in an object that's not currently in equilibrium. So, we are looking for F sub E, the equilibrant force. That's supposed to be an E. All right, now, here's where defining equilibrium in 2 dimensions changes slightly. This is our definition of equilibrium. Net force equals 0. In 2 dimensions, that means that we need to have equilibrium on both the x-axis and equilibrium on the y-axis. If we have equilibrium on the x-axis, a net force of 0 on the x-axis, and we have equilibrium on the y-axis, we will have equilibrium in both axes total. So, taking that idea and looking at the drawing that we just did, right, most of you could probably see how this one's going to go. If we're going to have equilibrium, if this is the resultant vector, if this is the combination of those 2 original forces, in order for us to get equilibrium, we're going to have to go something like this, right? Because that would cancel out the purple force and cause the net force to be equal to 0. But, taking it back to our definitions here of how we define equilibrium in 2 dimensions, hopefully you can see that, all right, If I have the total of this red component and this blue component on the horizontal axis, and they're both pointing to the right, I'm going to have a force that points this way. How big is it going to have to be? It's going to have to be 84.7 newtons. How do I know that? Because that's the sum of these two. Again, on the vertical axis, I have this blue component and this red component both pointing upward. That means I'm going to have something that counteracts those two that points in the opposite direction. How big is it going to have to be? 84.7. Guess what? We move this around here. Take this over here. I'm going to overlap some of my writing. And take this here. Oop, didn't make my green vector long enough. And that green vector, hey, look at that. It's the hypotenuse of a right triangle, where I know this side, and because of the forces and the angles that were chosen, I also know this side. Look at that. So we can save ourselves some time and effort because we know things like geometry and we know things like part A of the problem. And I now know that this force needs to also be 119.8 newtons. But again, I need to provide a direction. I need to know this angle theta. Your book generally measures things from the positive x-axis, so I can go something like this, okay? I know because of the sides here that this angle needs to be 45 degrees. I also know that the angle from the positive x-axis all the way over to the negative x-axis is 180. So in my head I do real quick, right? 180 plus 45, and I get 225. So the equilibrant force, remember we said the force required to cause equilibrium would be 119.8 newtons at an angle of 225 degrees if we measure from the positive x-axis, or once again, sig digs, 120 newtons at 225 degrees. That's our introduction to forces in two dimensions. Notice, concepts stay exactly the same, but how we address those concepts are a little bit different. Okay? So, next example problem is from that same page. Once again, page 152. And this time it's practice problem number 4. So once again, it says two forces are exerted on an object. A 36 Newton force acts at 225, and a 48 Newton force acts at 315. What are the magnitude and direction of the equilibrant? So, going back to what we talked about, magnitude and direction of the equilibrant. We are looking for F sub E, question mark, force of equilibrant. We know two forces. We know that there is a 36 Newton force acting at 225 degrees, and then we know that there is a 48 Newton force acting at 315 degrees. With that in mind, I'm going to go back to this page here, and I'm going to steal my coordinate system. And I'm going to bring it over here. So there's my coordinate system, right? We said in two dimensions the coordinate system looks like an XY axis. So first thing I'm going to do is I'm going to put my two forces on there. So F1, 36 Newton force at 225 degrees. That's going to look something like this. Okay? Then F2, 48 Newton force at 315 degrees. 315 degrees starting at the positive x-axis, 90, 180, 270, that's another 45 degrees. They make our lives easy. And so we take this, but now this force is going to be longer than that one, right? Because it represents 48 newtons worth of force versus versus 36 newtons worth of force. Magnitude and direction of the equilibrant. As we discussed in the previous problem, in order to get equilibrium, we need to have net force equal to 0. But in 2 dimensions, that requires that we have both equilibrium on the x-axis and equilibrium on the y-axis. So, first thing we're going to do, these forces, F1 and F2, are not horizontal forces and not vertical forces, right? They are a combination of 2 things, right? F1 is a combination of this horizontal force and this vertical force. F2 is a combination of this horizontal force and this vertical force. And we can now figure out what these forces are because we know our trig identities. So, once again, just for the sake of clarity, I'm going to take this here, I'm going to take this here, and I'm going to take this here. Okay? We know that this is 36 newtons, and this horizontal component was along the negative x-axis, which was 180 degrees from the positive x-axis, so that means that to get to the actual force, that's 45. And we can bring that over here, right triangle, 45, 45, 90, super easy. Once again, this blue force, for clarity, I'm going to take that here, I'm going to take that here, I'm going to take this here. This vertical component along the negative y-axis, which is 270 degrees from the positive x-axis, and that means that this is 45 degrees, but it also means this is 45 degrees. Now, you don't have to make this, you can make either one of these triangles. You can make this triangle like this, or you can make this triangle like this. It does not matter. And so once again, 45, 45, 90 triangle. This is a right angle, super easy. I'll give you 1 minute and, oh, nope, not there. 1 minute to figure this out, and then we'll be back. Go. Okay, so 45, 45, 90 triangles, the 2 sides are the same. Now, taking it back to our picture, this one goes here, this one goes here, this one goes here, and this one goes here. Okay? And we know values of all those forces. We'll reference those values in a second. Okay, back to the question at hand, magnitude and direction of the equilibrant. So let's take a look first at the y-axis. On the y-axis, there are 2 vertical components, this red one, this blue one. They both point in the same direction, meaning that they would combine in a fashion like we know how forces combine in 1 dimension, and we'd stack them up kind of like this to produce one big vertical component because they're both acting in the same direction. That means that if we are going to produce equilibrium on the y-axis, we need to have a force that counteracts the 2 of those together. So it's got to start here and it's got to go all the way back up here. This green dotted would counteract the two vertical components of those two original forces. And because we know that this one's 25.5, and because we know that this one's 33.9, we can figure out how long that green one has to be. We plug it into our calculator, 33.9 plus 25.5, and we end up with 59.4. Now, the x-axis is a little bit trickier because we've got two horizontal components as well, but they point in opposite directions. So they already start to cancel each other out a little bit. So if I take this one over here, that means that a good portion of the blue horizontal component is already canceled out by the red horizontal component pointing in the opposite direction. Therefore, my green horizontal component, in order to produce equilibrium on the x-axis, I only have to make up this much of a difference. And I can figure out how much that difference is because I know that the blue one is 33.9 and the red one is 25.5. So in this case, because they point in opposite directions on the x-axis, I'm going to subtract and I'm going to find out that my green one only has to be 8.4. So if I take it back to my problem, I might run out of room. I'm going to run out of room. Grr. I'll just move it down here. I know now that I have to have a force, move my timer out of the way, I have to have a force that acts both upwards at 59.4 and to the left at 8.4. Just like we did before, we need to find the resultant vector of these two, because this solid green is a combination or the combined effect of this 8.4 and this 59.4. So, first things first, because this is a horizontal component and because this is a vertical component, that means that I know that has to be a right angle, and I can figure out the magnitude of this value pretty easily. So I use Pythagorean theorem and find out that the magnitude of that side comes out to be 59.99. I'll write that. I know it's the wrong sigdigs, but I'll go with it. Okay? Now here's where it gets a little trickier, because we still got to have a direction. Remember, if we're finding a force, right, the equilibrant force, it has to have a magnitude and a direction, right? It says so in the problem. So that means I am looking for an angle. Generally, we start with the angle that's closest to where we started from. So, you know, in the way I drew this triangle, I went up first, and then I went sideways. I could have made the other triangle. I could have went sideways first and then up second. This one gets us an angle that's closer to the positive x-axis, right, if we would take it back up to our original xy axis. So I'm going to go with this angle. Okay? Now, we know a bunch of things about this triangle. So there's a lot of ways that we can figure out what that angle should be. All of them, though, are going to involve using one of our trig identities. So I'm going to take and I'm going to use tangent. I'm going to use this opposite side of the triangle in relation to the angle that we're looking for, and this adjacent side. So I come back and I remember that tangent theta is defined as opposite over adjacent. I know a couple things in this formula. I know what the opposite side is of the triangle in relation to that angle. It's 8.4 newtons. And then I know the adjacent side. It's 59.4 newtons. So I'm going to plug those values in here. So tangent theta is equal to 8.4 over 59.4. You don't have to do this every time. I'm doing it because I'm showing you how to do it the first time. In this case, theta is my unknown. That's what I'm looking for. I want to know that angle. I know the two sides, so this equation only has one unknown in it. So the first thing I'm going to do, I'm going to simplify just a little bit and go tangent theta is equal to, this is a fraction over here. I can figure out what that value is. I plug it into my calculator and I get that tangent theta is equal to 0.141414, etc., etc., etc. Now, I got to get theta by itself, so I need to get rid of the tangent part over here. That's where your inverse tangent function comes in. If I take the inverse tangent, or tangent to the -1, which is, underneath, okay, I'm going to cancel this tangent here. And that's just going to leave me with theta on the left-hand side. But if I take the inverse tangent of one side of the equation, I got to take the inverse tangent of the other side of the equation. On your calculator, that's where you hit the shift and then hit the tangent, or second, and then hit the tangent button. And that should show up as tangent to the -1. And then you plug in the value, 0.141414, repeating blah, 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 blah. You hit enter, and you find out that theta should be 8.049. Okay? So, getting back to our original question, what is the equilibrant? Well, I learned that it had to be 59.99 newtons, and then I learned that the angle at which that force has to act is 8.049, but that's 8.049 from the positive y-axis, which I know is 90 degrees from that, so that would be 98.049 degrees from the positive x-axis. Sig digging it up, right? That would give me 60. Got to make sure that that's significant 0. So 60 newtons at 98 degrees. Okay. That is the force that would produce equilibrium, that would counteract those two forces that we originally drew. If you want to check it out, you don't have to do this. I'm going to do it. You don't have to. Right? But if I get rid of some things, like all of this, all of my writing here, and just take a look at my forces, here's my green force. Ooh, off the page. This is taking longer than I wanted it to. It's the end of the period. I'm sure you're quite patient at this point. It's Friday too. I'm sure that's, adding to your patience. But there's the green force. That's the answer that we originally got. Here's the red force. That was one of the original forces they gave us, and here's the blue force. Taking a look at these three forces, would you say that they cancel one another? Well, red and blue both point down, so green's got to point up, but it's got to point up a lot more than red and blue point down because it has to counteract both of them. And then as far as the sideways part, red's pulling to the left, blue's pulling towards the right, so green's got to pull towards the left, but just not quite as much. So there we go. As far as some homework goes, sorry, should have had this pulled up. On the way in today, you should have picked up this problem set that after a long delay will eventually show up. Stand by. Stand by. There it is. Equilibrium in 2 dimensions. If you flip it over to the back side, problem 7 and problem 8 are very similar to the problems that we did in class today. And on the calendar, you can see that for December 14th, homework, problem set number 7 and 8. Also, you can see the answers to that problem set are posted online. So, good luck. If you have questions, check the answers online. I'll be back on Tuesday, so Monday we'll have another video introducing another kind of equilibrium in 2-dimension problem, and I'll bring it back on Tuesday.